2020. Thank you for the introduction. I am Diederik Wortman. I will provide a short talk in line with today's theme, which is, of course, software cost estimation and the need for sizing. I'm gonna talk about a software estimation challenge that was hosted recently. So at the 30th International Workshop on Software Measurement, or IWSM for short, and a combined effort with the Mensura conference, a challenge was hosted, and the point of this challenge was to stimulate good estimating practices and to provide an interactive discussion, so a discussion platform in the context of estimation during the workshop. So a little bit more about the conference itself. It's attended by both researchers and practitioners in all fields of software measurement. And while the workshop deals with many software measurement topics, this year's focus was on cost estimation and control, which lines up quite well with this year's Nesma conference theme. Again, the point of the challenge was to stimulate good estimation practices and to provide a discussion platform. And today I will discuss the solution developed by Metri. And I think it's important to mention that the point of the challenge was the estimation process and not so much the results. So that's the reason I will mostly discuss process today instead of a top-down focus on the actual results from the process that we followed. So I think that's good to clear up. I'd like this opportunity to introduce the team as well. We worked with a team of 6 with a mix of talents and skills during the challenge. We had people that were skilled in sizing, we had people that were skilled in consulting, we had people that were skilled in cost estimation. So it was a good mix. The names are over here. And this slide may confuse you a little as a cinema, but the theme of the challenge was to provide a development effort estimation for a movie manager information system. So the goal of the movie manager system is to store information about movies, actors, producers, directors, etc., and to query this data. That was the theme. It was a pretty simple information system that that was the objective and the subject of the estimation challenge. So the team I just introduced, we all work for a consultancy firm called Metri. We are based in the Netherlands, and as stated here, benchmarking and facts are in our DNA, and we help our clients by providing fact-based advisory such as benchmarks and cost estimations. We do this for the complete IT stack, from connectivity to infrastructure to application services. Today's talk is mostly relevant to our IT intelligence unit, which deals with the health and performance of software and software development and maintenance teams. So we have a proposition, the estimation suite, which deals with cost estimation for software. So that's about Metri. A little bit about myself. I'm a benchmarking consultant, active in actually all 3 units of Metri. And what I like to do is to combine the quantitative analysis with consulting in the complete IT stack. So to dive into the challenge a bit and also to provide structure to this talk, I have outlined the main parts here as input, the tasks we were given, and the deliverables. The host of the conference provided us with software requirements at a high level and a description of the development and deployment environment, so a bit more technical details. And the goal of the challenge was to provide an effort estimation to develop this software system. And during this talk, I will go through each of the 3 tasks in turn. So starting at the first task, I'd like to talk to you about estimating the size of functional requirements. So in order to determine the size, we used a number of different approaches. They're listed here. Some of these approaches are quite high level, such as the 2 here at the top. It starts at the data model and it converts. It's an indicative Nesma function point calculation from the data model to a function point, or the easy estimate in the cosmic measurement method that splits the software requirements into classes in order for quick estimation of size. However, we also did a detailed function point count by using the cosmic method, and we'll dive into that a little bit now. And when performing a detailed function point count, determining the required data model is often a good place to start. By attempting to create a logical data model of the requirements, we are forced to make assumptions about functionality that is not quite clear from the requirements that are provided. So requirements may be vague, they may lack details, they may actually skip some functionality, and by creating a data model, we are actually forced to work out or to iron out all the functionality that is still unclear. And a number of assumptions that you have to make, or that we had to make in this case, are provided here as an example. In the top, we have assumptions about the data, about relationships between the data, and here in the bottom, we make assumptions about the actual functionality of the user that were not quite clear from the requirements, but that you need to make anyway in order to reach a detailed function point count. So we used the cosmic functional size measurement method, and I'm quite aware that not everyone may be familiar with cosmic, so I'll provide a crash course in a minute. I'll explain the basics. Cosmic recognizes data movements that are elementary building blocks of software functionality. And this means that Cosmic recognizes processes and looks for instances when data enters the system, leaves the system, and is retrieved and stored by the system on arbitrary storage. So Cosmic divides the functionality of software into processes, and again, processes may enter data into the system, retrieve data from the system, write and read it from storage. And by counting these data movements, the entries, the exits, the reads and the writes, it is possible to reach certainty about the functional size of software. I think it's important to note that the functional user here is actually a quite abstract term and does not necessarily mean a human user, but may also be other software such as a hardware device or other software. So by counting these data movements, you are able to reach, you are able to measure the amount of functionality in a process. So that's Cosmic. It's a Cosmic crash course. Of course, the real method goes quite a bit deeper, but to get the gist, what you can do is start from a requirement that was given in the details of the challenge, work out user stories one level deeper, and from the user stories, work out functional processes. And these functional processes are the building blocks that Cosmic measures. Here in the columns, you may find the entry, the exit, the read, and the write, which are the building blocks of Cosmic measurement. And by taking the sum of these building blocks, you reach a functional size. In this example, it shows a detailed count for one of the requirements, which was there's a person object, which should be considered a logical table for those that are familiar with logical data models. And when this is repeated for all requirements, you take the sum of the Cosmic function points and the total functional size is determined. So that is how we estimated the functional requirements for the functional, we determined the size for the functional requirements. Moving on to task 2, which was to estimate the size of the non-functional requirements. And 2 separate non-functional requirements were actually provided to us. one regarding data validation, and the second one regarding user authorization, which deals with security. So to be able to estimate the impact on the size of the software to be developed, we had to state a number of hypotheses or assumptions on the implementation of these non-functionals. So all that was given to us were these non-functional requirements, and we had to translate this into impact onto the functional size of the application. And due to the length of the presentation, I will not go into detail of these assumptions or hypotheses that we had to make. However, one consequence was that we had to add a user object that allows the storage of user data to allow the user to be authorized before adding data to the system. So to work out task 2, we started with the functional size of the functional requirements, and after writing down how to implement the non-functional requirements, you are actually able to measure those as well functionally. And the bottom line is that these non-functional requirements and hypotheses actually result in some amount of functionality to be added to the system. That can be measured, and that's what we did. So the table on this page shows the original functional size on the left and the additional size due to non-functional requirements to the right. And in our case, the cosmic method allowed us to very elegantly actually account for all non-functional requirements and the assumptions that came with them, which means we were very confident in the measured size because we had a 100% accountancy for the non-functional requirements. So again, for task 2, where we measured the non-functional requirements, we used a number of different methods to determine the full size of the requirements, this time introducing a number of new approaches, such as the iceberg transformation, which tries to extrapolate the data that you don't know, as well as the more detailed function point count as explained. And finally, we ended up with a very likely estimation of 127 cosmic function points as the most likely functional size for this piece of software, given the functional and the non-functional software requirements. So with these tasks 1 and 2 completed, we have a pretty accurate idea of the size of the software to be developed in both functional and non-functional terms. And this means that we can use this as input for our effort estimation, which is the point of task 3. So I'm going to move on to that. To determine the effort required to develop the requested piece of software, and we use benchmarking data sets to provide us with reference data of similar projects, of course, already mentioned by a few other panelists today. In our case, we had 2 suitable databases available to us. The ISBSG dataset, probably familiar to most people here, and our proprietary Metri database. So because we have the sizing and other parameters available to us, we are able to quite accurately select similar projects in both datasets. And the most important metric we're looking for here is the project delivery rate, which is the amount of hours per delivered function points. So that's the inverse of productivity. And here on the right, you can see the results of this metric for both databases. On the y-axis, the effort hours divided by the number of function points for 3 different percentiles. So now we have the project delivery rate based on the benchmark data, but an estimate should take into account a number of other factors. And Nesma and the Association for the Advancement of Cost Engineering have developed a basis of estimate, which is quite common for many industries when doing cost estimation, and since it has been developed also to be used in the IT world. So the basis of estimate is a best practice to baseline a cost estimation and to check if all necessary parameters and other aspects of an estimation have been accounted for. So in our case, we have some red areas, and all of these red areas deal with cost. They're red because a cost measurement or cost estimation was not in scope for this assignment. But basically, the point of the basis of estimate is to provide a baseline to account for all different aspects of cost estimation. So it is important to reiterate what other panelists have already discussed, is that cost estimation is actually a probability distribution. And after this probability distribution has been developed, it is a choice which percentile, which is a choice along this x-axis, is selected to provide a y value to, in the left case, find the number of hours required to develop the software, or in the left case to look for the number of months, so the project lead time. Based on the amount of risk you are prepared to accept, you can find a value for either the hours or the lead time. Based on your choice on the x-axis, you will find a y value. So our experience tells us that 70% or maybe 75% around this area is an acceptable risk percentile for commercial IT projects. So that will, for us, be a likely value to select as a value for our estimation for both the effort and the schedule. So because this estimation is a probability curve, it is possible to provide a low, a likely, and a high estimate for the project in both the throughput, or actually the lead time of the project, and the number of hours required to perform activities. And here we have split them into 4 different activities, which are design, coding, testing, and implementation. Some more details about the activities in scope are here. And I guess the point here is that make sure your estimation is a probability curve, and make sure you go for a likely scenario instead of just the 50th percentile, which still means you run a 50% risk of overshooting your estimation. So to summarize, this year was the first of hopefully many more estimation challenges hosted at the IWSM. This challenge aims to stimulate good practice of cost estimation in the software industry. We attended with our Metri team because we want to promote these values of good cost estimation in the software world, and we want to encourage more groups to join the challenge in the future. So if there are people listening here that are interested in this challenge, be sure to keep an eye on the IWSM for next year, as there might be plans to reintroduce the challenge recurringly. So in summary of our process, we used multiple methods to measure a likely size for the software with the given requirements. We determined a probability curve for the effort and project lead time. These were based on multiple benchmark databases, in our case, the ISB's cheese set and our own Metri set. And furthermore, to account for all parameters and aspects of a cost estimation, we used the basis of estimate to assure reproducibility, verifiability, and defensibility of an estimation, which is very important for us. And finally, a note on the feedback received from the jury. So there was a jury judging the estimations. And our jury feedback focused on enthusiasm about multiple measurement methods. They appreciated the use of probability and uncertainty in our estimation, and thought the basis of estimate was elaborately analyzed. So they were quite happy about that. And that concludes my talk. I'd like to provide the option to ask some questions, maybe discuss some points mentioned today. And finally, I'd like to thank you for having me.
Okay, thanks, Diederik, for your presentation. Yeah, I think it's indeed an interesting subject to have this on the IWSM. One question I have is: was the other teams, did they estimate the same case, or was it another case what they estimated?
So I'd like to start with, there were two groups of teams. So there was a student challenge and a practitioner's challenge, and each group. So within the group, the challenge was the same, but the students' challenge was they focused more on an academic approach using regression analysis, and the practitioners had a more elaborate challenge to follow the complete process.
Okay.
But within the group, the challenge was identical.
Okay, and the results, were the results comparable, or was it compared what the results were with respect to the estimate?
Actually, the results varied quite a bit, but the jury did not focus on that much, as they commented mostly on the process and not so much on the results provided by the processes that were followed.
Okay, good. Okay, thanks a lot, Diederik. There's one question on I suggested you answer that on the Q&A. That's from Simon Wright. It's about the probability distribution function.
Yep, I've seen it. I will answer it.
Okay, great. Okay, thanks a lot.